So changing tack a little bit to talk about the radio astronomy surveys with ASKAP, and I'm presenting here on behalf of the 3 ASKAP survey teams that form the ASKAP Surveys project within ASTRO 3D. Though these 3 teams have a lot in common, and they certainly have common science goals that you'll see emerge as we go through the talk. In particular, we want to look at the amount and distribution of neutral hydrogen in and around galaxies, the connection between this neutral gas and star formation and galaxy evolution. And it's my view, certainly, that in a sense, neutral gas is a missing ingredient in our understanding of galaxy evolution, particularly as we move beyond the local universe. And so we'd really like to understand how H1, which is the raw material in many ways for star formation, links to the other properties of galaxies as we look across cosmic time. And of course, with H1 studies, there's also rich potential for dynamical analyses using H1 as a tracer of potential within galaxies. So let me see if I can go to the next slide. What do? Do I click or? How do I? Great, it's just a bit slow. So here is our telescope located in the Midwest region of Western Australia, a very remote site, deliberately so because it's a radio quiet site, and that really gives this one of the things that gives this telescope a really unique advantage for studying the redshifted 21 centimeter line of H1, because the site is essentially free of terrestrial radio interference, which means that the whole redshift range, with the exception of a small satellite band, which we can't do much about, is open to us. The other unique feature of this telescope is the phased array feed at the focal plane, which gives the telescope a 30 square degree field of view and means that neutral hydrogen surveys of the whole sky become a possibility. So potentially very large samples of galaxies observed in H1. Right. So that there are 8 survey science projects being carried out with the telescope. I've listed them here, but the 3 that are of interest for today are the 3 at the bottom here, the Wallaby Survey, Dingo Survey, and Flash. Many of these surveys, but not all, have names of cute Australian animals. And maybe to set the scene a little bit, I want to talk about the complementarity of these surveys and how they fit together to build up a unified picture of what's happening here all the way out to redshift 1. So the diagram on the left is taken from the original ASTRO 3D proposal and just shows how these surveys fit together. So in the middle with the green points, we have the Wallaby Survey. That's looking at the detection of H1 emission, the 21 centimeter line from individual galaxies. It's an all-sky survey detecting hundreds of thousands of galaxies in neutral hydrogen. So really potentially a revolution in the kind of data that we have for these studies. Then you see these narrow blue and yellow sort of cones. That's the Dingo fields. They're pushing out much deeper in integration time and up to higher redshift, with some direct detection of more distant galaxies, but also looking at stacking analyses that will allow you to say something about the average H1 emission properties of galaxies at redshifts where detection of individual galaxies and emission is difficult. And then right at the outside in red, going from redshift about 0.4 to 1, is the H1 absorption survey Flash. And that, as you'll see later on, is also detecting H1 in individual galaxies and in some cases apparently in extragalactic clouds. So before I go into the science, I just wanted to show a couple of slides to set the scene for the technical underpinning of these surveys, because they really bring a lot of challenges with them. So we had a milestone last month with the completion of 100-hour pilot surveys for all 8 of the ASKAP projects. And this is just a screenshot from a small celebration that the CSIRO team that run the telescope had on the evening when the last of these observations was done. And I'm showing this really just to highlight that there's an enormous number of people needed to keep this telescope running, keep it operating. especially on such a remote site. I also got one slide on the Pawsey Supercomputing Centre, and that's because there's really almost a symbiotic relationship between ASKAP the telescope and Pawsey the computer. The data rate that comes off the telescope is huge. It's a pathfinder for the SKA, and one of the things that it's tackling is the kind of data challenges that the SKA will face. So data come from the telescope at the top right here, come down optical fibers from the telescope all the way down to Perth, go onto a disk, get processed, and then eventually make their way after quality control into the data archive. So the issue we had here initially with the pilot surveys is that data flows into the disk from the telescope. It leaves the disk when it's processed and goes into the archive. But if the data comes in faster than it can be handled, then we have a bottleneck, and that for some time actually limited the rate at which we could observe spectral line data cubes with the telescope, because these spectral line cubes, as I've shown at the bottom here, are enormous. So a single 3D data cube, like the kind of data cube you would get from Muse, is somewhere between 900 and 1100 gigabytes in size. So the data flow is huge. And what we did in March and April with our colleagues from Pawsey, you see some of them at the left there with the science minister, is put in some extra storage to try and decouple the processing side from the data flow side, and that allowed us to finish fairly quickly the last of the H1 surveys. So those are the challenges we've faced along the way, but we're in the really good position now where we've got some fantastic data from the pilot surveys. It'll take 2 or 3 months for all that data now to be processed through the supercomputer and end up in the hands of the science teams. So a little bit of a status update since we last met in November. ASKAP has continued to operate throughout the pandemic so far. It's been operating since last year at full sensitivity with all 36 of the antennas. And as I've already said, pilot surveys, the first round of full sensitivity data for all the teams being completed. We have 6 ASTRO 3D funded researchers on the project, including Lillian Garrett-Smithson, who's a sensor Genesis postdoc also working on Flash. We've got around 10 students, and I'd like to highlight in particular the recent PhD completions by Ahmed El Ghali, Tristan Reynolds, and Jingjiang Shen. Publications can be found on the web, so I've just got the link there. Where we're at now is really the analysis of the pilot survey data, and we regularly present at conferences. Most recently at virtual conferences, we had the SK Pathfinders meeting FISC online last month, and just the last few days, Hein Yoon has presented results at the AAS meeting. So let me go on to the next slide. Okay, so coming to the Wallaby survey, Lister Staveley-Smith is the PI, and here's just an overview of the kinds of data they've been getting, starting with commissioning data with 5 or 6 antennas, working through early science observation with 10 to 24 antennas, and now the pilot survey observations that have been in progress since last year. Quite a number of early science papers have already come out of the Wallaby team, really with a focus on environmental effects and groups of galaxies, resolved maps of over 70 galaxies already published. And the point I'd like to highlight here from Lister's slide, Wallaby will very soon have gathered more H1 resolved data of galaxies than have previously been observed with all telescopes combined. So this survey is really taking us into a completely new place in terms of studying large numbers of galaxies in neutral hydrogen. I'm only going to show one more slide about Wallaby because we have some exciting pilot survey results coming up in the next talk from Tobias Westmeyer. But really just to orient you onto the sky, you see here the southern hemisphere. Wallaby is going all the way up to, I think, plus 30 degrees north declination. So you can see the 3 pilot survey fields here outlined in bright red. Some of the earlier fields observed also there. And in particular, this field on the equator is being observed both by ASKAP and by our collaborators with FAST, led by Dr. Wang. So we will look forward to seeing the combination of those 2 sets of data. Moving on to Dingo, Martin Meyer is the PI of this survey. They are looking at H1 all the way up to redshift 0.43. And again, the science goals here you can see similar to those of the other surveys. Mass assembly, they would like to measure the evolving cosmic H1 mass density and the H1 mass function, looking at, again, environmental effects, the ways that galaxies exchange neutral gas with their surroundings, and also detailed kinematic studies, angular momentum, scaling relations, and so on. So the slides that I'm going to show from Dingo are all provided by Zhongwan Ri, who's the ASTRO 3D postdoc, one of the ASTRO 3D postdocs working with the team. And this is just to orient you at where these Dingo deep and ultra deep fields are on the sky. The deep fields along the equator coinciding with the fields of the Gamma Galaxy Survey and the Future Wave Survey, and down here the ultra deep Dingo field is within the Gamma G23 region. So here are some early science results from Zhongwan and Martin for the ultra deep field. It takes only 2 pointings of ASKAP to cover the entire 60 square degree area of the Gamma 23 field. And you can see on the right here, these are all the galaxies for which there are optical redshifts and spectra available in the coned diagram. So processing, again, something of a challenge because of the size of the cube. And so what the team have done here is just to divide into chunks in spectral bandwidth, which correspond to chunks in redshift, and then analyze those chunks separately. So there are two main redshift ranges that will be looked at here, roughly one at redshift 0.04 to 0.06, and then one at slightly higher redshift from 0.06 to 0.08. And the experiment that's been shown here is an H1 stacking experiment. So taking the H1 spectra at the position of many hundreds of galaxies of known redshift, shift and add the spectra. That way you can beat down the noise and bring out the optical emission. So here you see the slightly lower redshift field with blue and red galaxies, and you can see some large scale structure there. And here's the more distant field. And again, you can see there's some concentration of galaxies towards the center of the field just there. Here are the results. So what we've got here, I've got two diagrams from Zhongwan. The first one is showing a comparison of blue and red galaxies. So the lower redshift range is on the left, the higher redshift range on the right. Plots here are for all the galaxies, then the blue galaxies stacked and the red galaxies stacked. And there's some estimates down on the side here of the characteristic H1 mass of blue galaxies and the red galaxies. What you see here is that the H1 mass, in terms of total H1 mass, then the blue galaxies are clearly detected, and the red galaxies also marginally detected. And again, at higher redshift, a similar H1 mass, but then becoming slightly harder with the numbers here to detect the red galaxies. Moving on to the groups versus isolated. So here they're looking at central galaxies, satellite galaxies, and isolated galaxies within those gamma fields. And again, you can see that there are detections in all three bins. And I think the top one is the central, and then we're going to the satellite galaxies, and then at the bottom, the isolated galaxies. So again, the lower redshift bin on the left, higher redshift bin on the right. And what you see here is that in terms of total H1 mass, the central galaxies have the highest H1 mass, followed by the satellites and the isolated galaxies. But if you actually look at the amount of H1 scaled by stellar mass, then it's the isolated galaxies that appear to be significantly more gas-rich in terms of their stellar mass. So this is really just a pilot study for the kind of work that could be done with much larger samples, and also at higher redshift once there are longer integration times on these fields. Finally, just the plot of cosmic H1 mass density, omega H1, and you can see, I think, in this purple box down at the bottom at quite low redshift, the preliminary result from Dingo early science, which is broadly consistent with other measurements in that redshift range. So it looks like the stacking technique is giving believable results in terms of the total amount of H1 at these redshifts. Okay, so Dingo is going well, and they've just started analyzing the pilot survey observations. I now want, in the last 5 minutes, to introduce the flash survey and H1 absorption. This is a kind of a 21 centimeter analog of the kind of optical DLA studies that people do with distant quasars. The difference here is that Lyman alpha absorption systems can only be seen above from the ground above redshift 1.7. We don't have any redshift restriction on 21 centimeter absorption other than simply the wavelength of range of the receivers. So again, this is going to be an all-sky survey, and we're looking at just some early results from commissioning and from early science. So again, quite a number of papers already from this group. During commissioning, we had observations of individual bright sources. In early science, with 12 antennas, we started looking at multiple sight lines in, again, one of the gamma fields. And we've had quite a number of detections so far. And I want to focus on this particular object, which is an intervening absorption line along the sight line to a background quasar, which Simon Weng will talk about a little later in this session. Just one early result from commissioning science that I've been involved in myself. So we looked along sight lines to 50 bright radio quasars, total redshift path length just over 21, and we detected 4 intervening lines, 2 of which were completely new, and all of which have estimated column densities that place them in the damp Lyman alpha range. So what you're seeing here is the plot of redshift going up from 0 to 5. This is not the cosmic H1 mass density, it's simply the number of damp Lyman alpha-like absorption systems along the line of sight. And you see as you go back in redshift that it's a modest increase in that. Numbers on the right are from ground-based DLA systems above redshift 1.7. The colored points down here below redshift 1.7 are from UV observations with the Hubble Space Telescope. Here in the blue circle is the redshift 0 measurement from H1 emission. And this blue point with the rather large error bars is the preliminary result from the ASKAP commissioning study. So there are large error bars here, but it's encouraging, first of all, that we make a significant number of detections, and also interesting that given the large error bars, we still seem to be somewhat above what the optical studies see, which may suggest there's a possibility of a dust bias in the quasar studies as you come down to redshifts around 1/2. Okay, last couple of minutes, an object from the gamma 23 field. So this was again a detection. We didn't know that there was a line there. We cross-matched bright galaxies in the gamma survey with background radio sources. This was the one detection, impact parameter of 17 kiloparsecs, column density just below DLA limit. And just on the right here, to show there's the gamma galaxy, the optical image. The radio source is shown by the contours here, 17 kiloparsecs out from the center of the galaxy. The galaxy itself is thought to be early type, so this would be a red galaxy, I think, in the classification that the Dingo people use, but in fact there's a lot of H1 out here in the outer regions, and you can even see, if you look closely, these blue star forming patches. So it does appear that this is a massive galaxy that's actually surrounded by neutral hydrogen, which is actively star forming, so it would seem. Pilot survey I'll run through very quickly because I know that time is getting on. So we're again looking at 32 different fields covering about 1,000 square degrees on the sky, and we're just starting to finalize the data pipeline and work our way through the vast amount of data that we have here. Just show some early results on quality analysis from Hein Yoon, who's Astro 3D postdoc. She's just looking at the continuum images at this stage for these different fields. That allows us to pick out the background sources that we're going to use for our absorption search. Couple of other related science projects, which I'll mention just very briefly. CFOG, which is looking at the relationship between X-ray absorption as measured by eROSITA, which is just starting its survey, and H1 absorption from ASKAP. We already know that these are related, that we can often see in neutral hydrogen in the 21 centimeter line, the same material which is absorbing the X-ray spectra of some of these active galaxies. And finally, we're setting up a consolidated database, a sort of value added information, because almost all the science we want to do with an absorption survey really requires combining with optical data to get the maximum science out. So Vanessa's also been working on this in conjunction with a Chinese PhD student, Renju Su, who's here funded by Akamai. So in summary, what I'd like to leave you with is that these large H1 surveys with ASKAP are really a revolution in terms of our knowledge about neutral gas and nearby and distant galaxies. I think it's a great tool for galaxy evolution studies. And in many cases, we rely very much on follow-up observations with optical telescopes and with instruments like ALMA and with the Genesis simulations. And I think Chris Power in his talk will touch on some of the work that Lillian's been doing in particular with H1 absorption. So these are really important tools for interpretation, and I think I hope that we'll see many opportunities for cross-project collaboration in ASTRO 3D. And that's where I'll finish. Thank you.